You don't go, huh? Good morning, all. Please help to share the Zoom, the link to YouTube. I've reshared it. Please, this is the YouTube link. So please share it. Please share the YouTube link. Please make sure you have put your details on the chat. Put your details on the chat. Likewise, those on YouTube. Put down your details on the chat. Thank you. So good morning and welcome to today's lecture. So today we continue with our FSC 1, 2, and SHM 101. I hope you can hear me. If you can hear me, please let me see a thumbs up. If you can hear me, let me see a thumbs up. Okay, thank you. So today we are going to start with chemical equations. As I told you the last time we met, we will also look at balancing, or how do we balance chemical equations. We are also going to look at stoichiometry calculations, limiting reagent, and the percentage yield. And at the end of today, what are you expected to have gained? So at the end of today, you should be able to balance chemical equations. You should be able to carry out stoichiometric calculations, and also be able to understand and apply limiting reagents to be able to calculate percentage yield. Now, talking about chemical equations, when we talk about chemical equations, we're actually looking at equations that will give identities and quantities of the reactant and the product. What are the reactants? What are the products? So a chemical equation will give you the particular identity and quantities of the reactant. It can also be said to be a symbolic representation of a chemical reaction in the form of symbols and chemical formula. So in another way, we can also say a chemical equation is a shorthand way of describing a chemical reaction. Instead of saying it verbally, 1 mole of oxygen reacting with 1 mole of hydrogen to give you 1 mole of water. So you can actually represent it by using a chemical equation, giving us the identity, what kind of element, and the quantity, how many moles. So you can also, so symbols and formula are actually used to represent the elements and compounds that are involved. So we have an example here. This is an example. This is methane reacting with oxygen to give us carbon dioxide and the water. If you look at this equation, you see that your methane and your oxygen are on the left-hand side, and we call this reactant. They are the ones reacting, methane plus oxygen. And if you look at the right-hand side here, is giving us what we call the product, that is water and the carbon dioxide. So from this equation, you see that you have the identity, your carbon, your hydrogen, and we also have the quantities. Carbon is 1, hydrogen is 4. So it will, as we said, it will tell you the identity, what kind of element, and the quantity. So your methane and oxygen, which are on the left-hand side, is actually what we refer to as the reactants, while the product, which is your CO2 and your water, are on the right-hand side, and they are the products. Another thing you should note is that atoms have been rearranged, bonds have been broken, and new ones are formed. If you see here, atoms have been rearranged. You have your C, carbon, hydrogen here, which is our methane. Here we now have our carbon, oxygen. So atoms have been rearranged. And the bond here was your carbon, hydrogen bond, but the bond here is your carbon, oxygen bond. So know that atoms have been rearranged, bonds have been broken, and new ones have been formed. So your carbon, hydrogen bond was broken here, and your carbon, oxygen bond was formed here. So we see that in a chemical reaction, atoms are neither created nor destroyed. And we said that they can only be changed from one form to another. So therefore, there must be same number of each type of atom on both the product and the reactant. If we go back to our equation, we said that atoms are neither created nor destroyed. Here you have your carbon here was not created, it was not destroyed. It was only it only went from one form to another, from your methane to your carbon dioxide. And therefore, there must be same number of each type of atom on both the product and the reactant. What do we mean by that? Your carbon here is 1. If you on the reactant, your carbon here is 1. Your hydrogen here is 4. Your hydrogen here is 4. 2 times 2, 4. Your oxygen here is 4. 2 times 2, 4. Your oxygen here is 2 plus 2 here. So the number of the quantity on the left-hand side must equal the quantity on the right-hand side. So that is why we say that, therefore, there must be the same number of each type of atom on both the product and the reactant. So this process of making sure that this rule is obeyed is what we call balancing a chemical equation. So just as I've explained, that in balancing chemical equations, the identities of the reactant and product must not be changed. Here, we had water. If you look at the equation here is water from methane and the oxygen. So what we are trying to say is that if you have water, hydrogen is 2, oxygen is 1. Here, hydrogen is 2, oxygen is 2. So this is your hydrogen peroxide. You cannot form something new. Or here now you now have hydrogen 4, oxygen 2. Your hydrogen is 2 here, your oxygen is 1 here. So whatever you are forming here, your hydrogen must be 2 and your oxygen must be 1. Also here, your oxygen is 2, and here your oxygen is 3. So this is your ozone, and this is your oxygen. So what we are trying to say is that subscripts cannot be changed, nor atoms be added or removed. You cannot add another atom. You cannot have H2O here, and you now have H2Cl. You cannot add a new atom. Even the subscript, you cannot have 2 here, and you're not coming here, you're having 4. No. Subscripts cannot be changed, nor atoms be added or removed. So also, most chemical equations can be balanced by inspection, that is trial and error. Nobody has a monopoly of knowledge. They give you a chemical equation to balance. It's an equation you have not seen, but there's a way you can go about it to be able to balance it. That is why we say that most chemical equations can be balanced by inspection. That is trial and error. It is just a trial and error. So it is always best to start with the most complicated molecules. That is the molecule with the greatest number of atoms. So I will look at one example before I go to the next slide. Yes, so, okay. So if you have, let's say you have your potassium chlorate plus, sorry, your potassium chlorate sorry, this is an arrow. I don't know why it's not working well. Okay. Going to your potassium chloride plus oxygen. If you look at this equation, is it balanced? So, is it balanced? I want you to put it on the chart. I will say no. So here on the reactant, we have potassium is 1, chlorine is 1, oxygen is 3. Why here potassium is also 1, chlorine is 1, but your oxygen here is 2. Oxygen here is 2. So we see that this equation is not balanced. So how do we balance this equation now? How do we, so you can say, okay, potassium is balanced, chlorine is balanced, on the right, both of them are balanced, it's only the oxygen. So what do we do? So if we put 2 here, so your potassium here will now be 2, your chlorine will also be 2, isn't it? But that means we also have to put 2 here. So your potassium here is also 2, your chlorine is also 2, your oxygen is now 6. That means you have to put 3 here. So what it means that your oxygen here is now 6, and your oxygen on the product is also 6. So that is how to balance your chemical equation. Okay. So let's see what we have on the next slide. Okay. So this is what we have. So this is actually what I tried to show so that you will understand how we can balance equation by looking at the number of atoms on the reactant and with the number of atoms on the product. So you have seen how I did it. First of all, I looked at the equation without adding anything to see if it's balanced. When I checked it, I saw it was not balanced. So I started doing trial and error to be able to make sure that my equation is balanced. So this is now the balanced equation. So that is actually, so you see that your potassium is now 2 here, your chlorine is 2, your oxygen is 6. And so so this is actually the final how you check. But you see, when I did it, we started with 1, 1 to see if it was balanced. So now, this is the classwork. Balance the following chemical equations. I want you to do the first one. Everybody, using the method I showed you. So here, nitrogen is 2, oxygen is 5 as the reactant. As the product, nitrogen is 2, oxygen is 6. That is 4 plus 2, 6. So can we balance this equation? I give you just 2 minutes. Balance the first equation. The second one, you are going to do it as a homework because we don't have all the time today. So I'm waiting. Balance the equation. Put it in the chat. Balance the just the first one. Balance this chemical equation. Okay, so we just need to add 2 to our your nitric acid. Okay, thank you very much. Thank you those on YouTube. I can see your answers also. Okay, thank you very much. I can see you all got it correct. So that's fine. Now, so that is that for balancing of your chemical equation. It's not something so difficult. So if you understand, that was why I took time to do it instead of just showing you the slide. So with that, you'll be able to understand how to balance your chemical equation. So the next is your stoichiometric calculations. When we talk about stoichiometry, we're actually talking about the relationship between the masses of reactant and product before, during, and following chemical reactions. I will take that again. When we talk about stoichiometry, we are actually looking at the relationship between the masses of the reactants and the product before the reaction, during the reaction, and following the chemical reactions. So before performing any stoichiometric calculation, the equation must be balanced. You must balance the equation for us to know that, okay, it is actually 1 mole of your hydrogen that is reacting with 1 mole of your oxygen to give you 1 mole of water. It is very, very important to balance the equation. So you must know how to balance your equation. So here we have our propane. We have 1 mole of our propane reacting with 5 moles of your oxygen to give you 3 moles of carbon dioxide and 4 moles of water. So this shows that this equation is balanced. So I would have asked you to balance this equation, but as I said, we don't have all the time today. So that is actually what we mean by stoichiometric calculations. You must first of all balance the equation to be able to know the number of moles that is actually reacting. So from the equation on the previous slide, what mass of oxygen will react with 96.1 grams of propane? What mass of oxygen will react with 96.1 grams of propane? As we said, first of all, we balance the equation. Then from the balanced equation, set up the appropriate mole ratios. So if you look at this ratio, we have, that the ratio of your propane to your oxygen is ratio 1:5. So 1 mole of your propane is actually reacting with 5 moles of oxygen. So the ratio is ratio 1:5. So step 3 is that convert the non-masses of the reactant or product to the moles of that substance or vice versa. So 1 mole of your propane is 44.1. How did we get 44.1? That is a 12, carbon is 12 times 3 plus hydrogen is 1 times 8. That will give us 44. 1 mole of oxygen is 32 grams. How did we get 32? Your oxygen is 16 times 6. That is 32. 5 moles of oxygen. That means your oxygen here is 16 times 2, which is 32 multiplied by 5. That is 160 grams. So what it means is that 44 grams of your propane reacted with 32 grams, reacted with 160 grams because the oxygen here is 160. So 44 grams of your propane reacted with 160 grams of your oxygen. So that 1 mole of your propane reacts with 5 moles of oxygen. Invariably, 44.1 grams of your propane react with 160 grams of oxygen. And what is the question? The question says that what mass of oxygen will react with 96.1 grams of propane? From the equation, that is from the stoichiometry, we already know that 44 grams of propane will react with 160 grams of oxygen. Now they're asking us 96.1 grams. What would that give us? That would now be 96.1 times 160 over 44.1, and that will give us 349 grams of your oxygen. Please, is anybody confused at this stage how we got 349 grams? So it's just from stoichiometry that we're able to get that, that answer. From the stoichiometry, how many moles of propane reacted with 5 moles with oxygen to give us your CO2? And that is just that is what we have tried to do. From the equation of the previous slide, what mass of oxygen will react with 96.1 grams of propane? From the equation, we have already known 1 gram, 1 mole will give us 5 moles. invariably 44 gram will give us 160 gram. Now 96.1, this is common arithmetic. I don't think there's any much problem with this calculation. Now, we have a practice question here. This is your sodium carbonate. Your sodium carbonate reacting with your citric acid to give you your carbon dioxide and your water. And your sodium citric. So now, the question is, so from this equation, you see that is one mole of your sodium carbonate reacting with 1 mole of your citric acid to give you 1 mole of each of the products. So we've already, from the equation, that is why we say that, first of all, you have to balance your equation. You might be given an equation that is not balanced. The first thing you are going to do is to balance your equation. And that is why that was the first thing we did on how to balance your equation. Now, if you look at this equation, your equation is already balanced. So the question is now, what mass of your citric should be used for every 0.05 gram of your sodium carbonate? And from this, and again, what mass of CO2 can be produced from such a reaction? So if you look at this equation, we know that 1 mole of our sodium carbonate will actually give us 1 mole of our citric acid. So, okay, so I think I will have to use my, it's a practice question. Let me just do the first one for you. Let's just do the first one so that we understand. I think if I ask you to do it, I know you can do it, but for those that will not be able to do that, so we have our sodium hydrogen carbonate. We have our sodium hydrogen carbonate. Okay, so, okay, yes, we are going to balance the equation. So I would have asked you to balance the equation plus your C6H8O7. I'm happy we are following. So this will give us sodium 3, C6H5O7 plus CO2 plus H2O. So how do we balance the equation? We just add 3. We put 3 here. So your sodium here is already 3. Your CO2, you also have 3. And your water, you also have 3. I think that is the balanced equation. Are we okay with that? Are we good? Okay, so we had told this is how to balance the equation. You should be doing that yourself. You should be balancing the equation because I've already taught you how to balance the equation. So now, we don't really have much time again. Well, it's fine. It's just for you to be able to understand. So I expect you to have balanced the equation. So what it means is that 3 moles of your sodium hydrogen carbonate will react with 1 mole of your citric acid from the equation. So 3 moles of your sodium hydrogen carbonate will react with 1 mole of your citric acid. So if you, so 3 moles of your sodium hydrogen carbonate, if you do that calculation, I think you are going to have your sodium hydrogen carbonate. We already have 3 here. That will give us about 156 grams, if I'm correct. And 1 mole of your citric acid, which is your C6H8O7, their mass will give us, I think, a 192 grams. So what it means is that 156 grams what is the problem? Of course, now hydrogen is 6. Hydrogen is how many? 8 plus 3, 8, 9, 10, 11. On the product is also 11. If you look at your water, water has 3. 2 times 3 is 6 plus 6 plus 5. That is 11. Please, so that we can continue, it's balanced. If it's not balanced, I will not be writing it for you. So we have just, so 156 grams of your sodium hydrogen carbonate will give us 192 grams of your citric acid. Well, you can do that calculation. Sodium is 23 times 3, that should be 69. Hydrogen is 1 times 3, that is 3. Your carbon is 12 times 3, that is 36. Your oxygen is 16 times 3, that is 48, times another 3. Okay, yes, you are right, times another 3. Thank you very much. That's 225, you are correct. So that would be, your oxygen is 16 times 3, that is 48. 48 times another 3, that is 250. Is that 252? Okay, that's correct. Thank you so much. So that is 252. Thank you. 252. So what it means that 252 grams will give us 192 grams. Therefore, 0.05 grams will give us what? You can now do that calculation. So that is how to answer that question. So for the mass of your carbon dioxide, the mass of our carbon dioxide should be around, if you do that calculation, that should be about 132 grams of your CO2. 132 grams, if I'm correct with that calculation. So let's go back to our slide. Okay. So I've tried, this is the one we did, calculating the mass of this, of course, by balancing the equation. It's supposed to be a practice question. That was why I did not balance that equation here, but I had to balance it for you. So it's a practice question. So we'll be able to do this, balance the equation. So we got 252 grams of this reacting with this, but they're asking us for every 0.5 grams of your sodium your sodium carbonate. So what mass of citric acid should be used for every 0.05 grams of your sodium hydrogen carbonate? So if you have 192 for 252, then 0.05 will give us what? So that is how to answer the question. Then what mass of CO2 can be produced from such a mixture? So from this mixture, what is the mass of CO2? When you balance the equation, you'll be able to get the mass of CO2 that can be obtained from this mixture. I think I've already given you the answer. So please try out these questions. I think I've already done the practice question for you. Okay, this is another practice question. This is your obtain reacting with oxygen to give you carbon dioxide and water. So this is already balanced. You say how many moles of CO2 are produced when 2.0 times 10 raised to the power 10 mole of your octane is burnt? I'm not going, this is a practice question for you. How many moles of CO2 are produced when this mole of your octane is burnt? From this equation, we see that 2 moles of your octane is actually giving us, this is 25. It's actually giving us how many moles? 25 moles of oxygen, 16 moles of CO2, and 18 moles of water. Now they're asking how many moles of CO2 are produced when 2.0 times 10 raised to the power 10 mole of your octane is burnt. So what it means is that 2 moles of your octane is actually giving us 16 moles of your CO2. Now they're asking you how many will be produced when you use 2.0 times 10 raised to the power 10 mole of your 2.0 times 10 raised to the power mole of your octane is burnt. This is just pure stoichiometry. This is very, very easy. Can we do this now? Everybody, can we do this and let me have your answer? This is very straightforward. From the mole ratio, you already have the number of moles. So can we do that and let me see your answer immediately? Just the first one. 2 moles of your octane is actually giving us 16 moles of your CO2. So they are now asking how many moles of CO2 are going to be produced when you use 2.0 times 10 raised to the power 10 mole of your octane. Can I see your answer? Can I see your answer? Correct. 1.6 times 10 raised to the power 11 moles. Thank you very much. That's correct. So I'm glad at least we are following the calculation. So you can do the second one. As I said, it's supposed to be practice question, but I just wanted you to do it in class so that I'm sure you understand what we are doing. So that is for your chemical reactions, your equations, and your stoichiometric calculations. So you see that you can actually get your answer from stoichiometry. So if you look at this question, you see that this question is very, very easy. It's just from stoichiometry. So once you know the number of moles, you can be asked using the number of moles, and you can also be asked using the gram. If it's using the gram, you just convert this to gram and convert this to gram. And that means the question here will also be in gram. It's just simple stoichiometry. Now, let's go to limiting reagents. Because I told you that you have to use your limiting reagent to be able to calculate your percentage yield. And for you to be able to calculate your limiting reagent, you need the number of moles that we have already looked at, and we also need the mass of the compound. So you can actually calculate your limiting reagent either using the number of moles or the mass of the compound. When we talk about limiting reagent, what do we mean? Limiting reagent in a chemical reaction is a reactant that is totally consumed when the chemical reaction is complete. We can say that it is the reagent that is used up first, that is completely used up. Because you see, in most reactions, okay, look at this reaction. This is 2 moles of your octane, and this is 25 moles of your oxygen. Which one do you think will be used up first? That is what limiting reagent is telling you, that both of them are not completely used up. One is usually completely used up, while the other one is still remaining. So that is what we mean by limiting reagent. That is the reactant that is totally consumed when the chemical reaction is complete. That is, the amount of product formed is limited by this reagent. So what it means is that once that limiting reagent is completely used up, the reaction ends. So the limiting reagent is the determining factor for the product that will be formed and the quantity of product that will be formed. Once that limiting reagent is used up, the reaction can no longer continue. So I have an example here. In making toast bread, I know most of us will like eating toast bread, but it's fine. So making toast bread requires 2 slices of bread and 1 egg. Of course, most of us, that is how we make toast bread. Now, I want to ask you, how many toasts can you make if you have 20 slices of bread and 12 eggs? I want to know which one will be the limiting reagent, which one will be used up first, and after that, you can no longer make your toast bread. Can anybody answer that question? Toast bread. So let me go back. Since this is the first limiting reagent, I will do the calculation. So let's see. So we said that 2 slices, we need 2 slices of bread for 1 egg. For 1 egg. Now, for 20 slices, is going to be what? 20 times 1 over 2. 2 here, this is 10. So we need, for 20 slices of bread, we need 10 eggs. So 20 slices will require 10 eggs. But we have how many eggs? 12 eggs. So 2 eggs are in excess. Therefore, which is the limiting reagent? Your bread is the limiting reagent. Thank you very much. Thank you, those that did the calculation with me. Okay? So that is how you calculate your limiting reagents. So we go back to our slide. Are we following? If you're following, let's give me a thumbs up. If you are following, let me see your thumbs up. Thank you. So we move. So that is how to calculate your limiting reagents. So now, this is another example. 1 mole of your nitrogen reacting with 1 mole of your hydrogen to form what? 1 mole of ammonia. First of all, is this equation balanced? If it's not balanced, can we balance the equation? Let's balance the equation. How do we balance the equation? We just we add 2 here. We add 2 to your ammonia, and we add 3 to our hydrogen. So that means we have 6 molecules of hydrogen, 6 molecules of hydrogen, 2 molecules of nitrogen, and since we added 2 here, we also have 2 molecules of nitrogen. Now we have balance, because the first thing, whether you are doing, whatever calculations you are doing, first of all, balance the equation. If your equation is not balanced, your answer is going to be wrong. So if we have 35 kilograms of nitrogen and 15 kg of hydrogen, which is the limiting reagent? Which is the limiting reagent? So from our balance equation, we have 1 mole of nitrogen reacting with 3 moles of hydrogen to give us 2 moles of ammonia. So we want to know which is the limiting reagent. Is it the nitrogen or the hydrogen that will be used up first for the ammonia to be formed? And here we are looking at it in terms of kilogram. That means 35 grams, you are giving 35 grams of your nitrogen and 15 kilogram, 35 kilogram of your nitrogen and 15 kilogram of your hydrogen. Now, what is the limiting reagent? So from stoichiometry, do I ask you to do that calculation and give me the answer? The equation must be balanced. Set up a mole ratio. We already know the mole ratio. Convert the mole ratio to mass. So we are going to convert our mole ratio to mass because what we have here is there in kilogram. So can we do that calculation? And let's see if you can do that. And let me see. Let me have your answer. He said nitrogen will be used up first. How do you know? I want to know what is your value. Okay, we already have it here. I just wanted you to try it out. So as I said, 1 mole of your nitrogen will react with 3 moles of your hydrogen to give you 2 moles of your ammonia. So converting it to mass, your nitrogen will be what? Your nitrogen is 14 multiplied by 2 because it's just 1 mole. That will give us 28. Your hydrogen is 1 multiplied by, so your hydrogen here is 6. 2 times 3 is 6. So what it means is that 28 grams of your nitrogen will be required for 6 grams of your hydrogen. But here I told that we had 35. So 35 kilograms of your nitrogen will now be what? 6 times 35 over 28. So we need 7.5 kilograms of hydrogen. For how many were we given? We are given 15 kilograms of hydrogen. So from our calculation, which one do you think will be the limiting reagent? So which is the limiting reagent? Let me see your answer in the chat. From our calculation, nitrogen. Thank you. So that is how you know the limiting reagent. So what we need that we only need 7.5 kilograms of hydrogen, but we are giving 15 kilograms. So we still have some excess of your hydrogen. So invariably, the limiting reagent. So once 35 kilograms of your nitrogen is used up, then your ammonia will be formed, and that will be the end of that reaction. Sorry. So since 35 kilograms of nitrogen will only react with 7.5 kilograms of hydrogen, there will be excess of hydrogen. This then means that your nitrogen finishes first and is therefore the limiting reagent. So I have another question. And you're going to do this for me. This is very easy. Nitric oxide reacts with oxygen gas to form nitrogen dioxide. In that experiment, 0.886 mole of your nitric oxide is mixed with 0.503 mole of oxygen. Calculate which of the two reactants is the limiting reagent. That is the first one I want you to calculate. Calculate the number of moles of NO2 produced. So first of all, we have to balance the equation. So how do we balance? Can we write the equation? Okay, I have the solution. I would have asked you to do that, but let's go to the solution. It's very easy. I think this is the easiest. So this is the equation. Your nitric acid reacting with your oxygen to form your nitrogen dioxide. So to balance the equation, of course, here nitrogen is 1, oxygen is 2 here. Oxygen is 3 on this side, oxygen is 2 on this side. So how do we balance? To make, first of all, to make oxygen, to balance oxygen. So once we put 2 here, oxygen becomes 4. For oxygen to become 4, we already have 2 here. That means we have to put 2 here. For oxygen to be 4 here, and our nitrogen is already 2, and our nitrogen is 2. So you can, we already have a method that we use to balance the equation. So first of all, balance the equation. So we have already set up our stoichiometric ratio. So 2 moles of your nitric acid will react with 1 mole of your oxygen to give you 2 moles of your nitrogen dioxide. So we have a ratio, our mole ratio is ratio 2 to 1 to 1. Now the question is, the number of mole of your nitric acid is 0.886 mole, while that of your oxygen is 0.503 mole. Now from this stoichiometry, we know that 2 moles of your nitric oxide will react with 1 mole of oxygen. So what it means is that 0.866 moles will react with what? 0.866 times 1 over 2. That is 2 moles to 1. Then 0.866 will now be 0.866 times 1 divided by 2. And that will give us 0.443 moles. And how many moles were we given? We are given 0.503 mole of oxygen. So invariably, we still have some oxygen left. So your nitric acid, your nitric oxide, or your nitric acid will finish first, while your oxygen is still left. So your nitric oxide is therefore the limiting reagent. So your nitric oxide is therefore the limiting reagent. And the next question says, calculate the number of moles of NO2 produced. So I think you can calculate that, the number of moles of your NO2 produced. So let's look at your yield and your percentage yield. So before we go, please, can you calculate the number of moles of NO2 produced since we already know the limiting reagents? We know the limiting reagent. Can we calculate the number of moles of NO2 produced? Because we already know that your nitric oxide is your limiting reagent. So what it means that 2 moles of your NO2 is actually what is going to produce 2 moles of your dinitrogen oxide. So I want you to calculate the number of moles of NO2 produced. Can we do that? Since we already know the number of moles of our nitric oxide, because that is the limiting reagent. So that is actually what we are going to use to carry out that calculation. So from stoichiometry, you can even get that answer from stoichiometry. Oh, correct, 0.866, because you have 2 moles of this equivalent to 2 moles of this. If you do it by calculation, you are going to get 0.866. Thank you very much. So we move on to yield and percentage yield. When we talk about the yield, we are actually talking about the mass of the product formed in a chemical reaction. That is, when you carry out a chemical reaction, the product that you formed, when you weigh the mass using a weighing balance, that is the yield. That is the yield you have formed. So the mass of the product formed in a chemical reaction is called the yield. While the percentage yield refers to the percentage ratio of actual yield to the theoretical yield. So your actual yield is that yield that you have, that you have weighed, that you have synthesized, that you have produced. That is the yield. While the theoretical yield is we get it from stoichiometry. We are going to see how we are going to get that. So the amount of a product formed when the limiting reagent is completely consumed is called the theoretical yield. So your theoretical yield, you are going to get it from the limiting reagent, because it is that limiting reagent when it's completely consumed that will form that product. So it is that product that is formed, that is the yield. That is the actual yield. So the amount of a product formed when the limiting reactant is completely consumed is called the theoretical yield, while the actual amount of product obtained in an experiment is called the actual yield. So I will say that in most cases, the actual yield is not equal to the theoretical yield. What do we mean by that? That the actual yield most times is not equal to the theoretical yield, because your actual yield during your preparation, some things must have happened. Also, as you know, the limiting reagent, once it's finished, then that reaction stops. What it means is that you still have some unreacted materials because the other reactant is still there. So when you now get your actual yield, what it means is that, yes, that reaction is complete, but there is some other things, that there are some impurities that is still there. So most times, the actual yield is not equal to the theoretical yield, because the theoretical yield, everything is there. The number of moles, the mass is there that you are going to use from stoichiometry to get the theoretical yield. So most times, you see that your actual yield is usually smaller than your theoretical yield, because during the reaction, one or two things must have happened that will make that reaction for you not to get all the yield you need in that reaction. So to know the efficiency of a chemical reaction, the percentage yield is calculated. From the percentage yield, you'll be able to know if your reaction went to completion or your reaction did not actually go to completion. So percentage yield is actually actual yield, that is the product you get at the end of that reaction, over your theoretical yield, that is the mass you get from stoichiometry multiplied by 100. And we say that when the actual yield equals the theoretical yield, the reaction process is stoichiometric process. That means that what you did in the lab and what you came to do on the laptop is that is a stoichiometric process. That means from your stoichiometry, what you got is actually the same thing you got from your actual reaction. So we say that when the actual yield equals the theoretical yield, the reaction process is stoichiometric process. So you can say, oh, this reaction is actually stoichiometric process. As we said, most times the actual yield is not equal to the theoretical yield. The actual yield is most times is usually small. So we have a classwork here. This is your lithium reacting with your nitrogen to give you your lithium nitride. We've already balanced the equation. It's a classwork, so we've already balanced the equation so that we don't waste much time. So what it means that 6 moles of your lithium will react with 1 mole of your nitrogen to give you 2 moles of your lithium nitride. This is from stoichiometry. Now, I say, what is the theoretical yield of your lithium nitride? When 12 grams of your lithium, that means you were given 12 grams of your lithium and 33.6 grams of your nitrogen. So we are asking, what is the theoretical yield? That is the first question. It says, if the actual yield of your lithium nitride is 5.89 grams, what is the percentage yield? First of all, we are going to calculate the theoretical yield. Your lithium, because it's given in gram, so we are going to convert from our stoichiometry, we are going to convert this ratio to gram. Your lithium is 6.9 or 7, that is the atomic mass unit, multiplied by 6. Can we do that calculation for me? Then your nitrogen, of course, is 14, multiplied by 2, that would be 28. Don't worry, let me do the calculation. So this is the first time. So as I said, your lithium is let's use a 7. It's 6.9, but we can use 7 times. We had 6 of it, which will give us 42. And our nitrogen was 2, which will 2 times 14, which will give us 28. So what it means is that 42 grams of your lithium will react with 28 grams of your nitrogen. But we are given 12.3 grams. So 12.3 grams will give us what? So that, please, can you do that calculation? So we now have 12.3 times 28 over 42. I think that will give us about 8.2 gram. 8.2 gram of, thank you. So we have 8.2 gram of nitrogen. But how many grams of nitrogen were we given? 33.6 gram of nitrogen was used. So which one is the limiting reagent? Which is the limiting reagent? Put that in the chat. Lithium. Thank you very much. Thank you. Lithium is the limiting reagent. Lithium is your limiting reagent. Okay. Okay. So I think we can share our slide again. Okay. Okay. So from that, you see that your lithium is your limiting reagent. So that is the calculation I just did. Since lithium is a limiting reagent, it determines the amount of product formed. Now, the other question says, if the actual yield of lithium nitride is 5.89 gram, what is the percentage yield? So 6 moles of lithium will give us 2 moles of lithium nitride. So what it means that 42 gram of lithium will actually give us 70 gram of your lithium nitride. But we use 12.3 gram, which will give us 20.5 gram of your lithium nitride, because we are now looking for the theoretical yield. So as I said, for the theoretical yield, we are going to use the limiting reagent. We already know that our lithium is our limiting reagent. So 42 gram of your lithium is actually what is going to give you 70 gram of your lithium nitride, because your lithium nitride is the product. And we only use 12.3 gram of your lithium. So what it means is that we are going to get 20.5 gram of your lithium nitride. So this is actually the theoretical yield. So this is your theoretical yield. And we know that percentage yield is your actual yield over your theoretical yield times 100 over 1. We are given the actual yield as 5.89. So we now have actual yield 5.89 over 20.5 times 100 over 1. So our percentage yield is 28.7%. Our theoretical yield is 20.5 grams. So your limiting reagent is very, very important. It will help you to know the one that is in excess and the one that is the limiting reagent. So once you know your limiting reagent, you now use it by stoichiometry to now get your theoretical yield. So that is that for our lecture. Any question? So that brings us to the end of my class. So we'll take questions. So that is the end of Dr. Ejia's lecture. So we'll take questions. Let me go to the question and answer and see your questions. How is this 70 grams of lithium nitride? Your lithium nitride, well, your lithium is your lithium. If you do that calculation, you put 2 in that equation. Okay. What is the mass of this lithium nitride? Can you do that calculation for me? Can you do the calculation? Your lithium is, I said we are using 7. 7 times, this is 6. 7 times 6 is 42. And nitrogen here is 14, if I'm correct. 2 times 14, that is 28. Maybe it's my calculation that is wrong. Is it my calculation that is wrong? What is the mass of lithium, this lithium nitride? That is how we got 70 grams, my dear. Is that okay? You have the balance, you said Li to N3. Where did you get that balance of equation? You see, your equation is wrong. This is the balanced equation we are using, please. This is the balanced equation. I don't know why you put 2 here and they put 3 here. That equation is not balanced. This is your balanced equation. So that is how we got 70 grams of your lithium nitride. Any other question? Okay. You said, Ma, we don't understand the theoretical yield. You said, Ma, why didn't we check nitrogen for limiting reagent? You can check nitrogen for limiting reagents. You can, but depending on what you are given. I think what we are given is, once you are given you can check both of them for limiting reagents. What is the theoretical yield? Let me see the limiting reagents. You can check either one for limiting reagents. There's nothing that says that you cannot check oxygen. You can check either one, but the limiting reagent will always remain the limiting reagent. So let me see another question. Please, can you go to the getting the limiting reagents? In getting your limiting reagents, I think I took time to carry out that calculation, even using this is nitrogen, hydrogen, to give you. I think I took my time to carry out this calculation, writing it even before we came to this place. So now for you to know the limiting reagent is for you to be able to know the atom that is used up first. Now, you were given 35 kilograms of nitrogen, we are given 15 kilograms of hydrogen, and this is our product. First of all, you have to balance your equation. We are sure our equation is balanced. We know the mole ratio. Mind you, Because we are here, we are not using number of moles. We are already given the details in kilograms. So we have to carry out our calculation in kilograms. So here nitrogen, 1 mole of your nitrogen, if you look at this stoichiometry, you see that your nitrogen is 14 times 2. That is how we got 28. And your hydrogen is 6 times 2. Hydrogen is your 6 times 1. That is how we got 6. So what it means is that 6 kilogram of your nitrogen is going to react, 28 kilogram of your nitrogen is going to react with 6 kg of your hydrogen to give you your product. Now, we are given 35 kilogram of your nitrogen. What will that now give us? So that is how we got 6 will give us 28, then 35 will give us 35, will now give us 6 over 28 times 35, and that is how we got 7.5 kilogram of hydrogen. And how many kilogram of hydrogen were we given? 15 kilogram. So because we still have excess, that is why we say that your hydrogen is that is why you say your hydrogen is in excess. So your nitrogen will now be the limiting reagent because it will be used up first. And went ahead to carry out this calculation. So which other question? I'm checking this. Okay. Is actual yield always given in the question, or we will calculate in some questions? The actual yield will be given because the actual yield is actually what you have prepared. You cannot be given to unknown. You will be given the actual yield, so you can actually get the theoretical yield from stoichiometry. Because in an exam, you are not carrying out the reaction in the exam hall. So we've already carried out the reaction and we'll give you the actual yield. But in the exam hall, you can be able to determine the theoretical yield from stoichiometry. That is why the actual yield will always be given. It is the theoretical yield that you are going to determine from stoichiometry. So what we have here is actually the theoretical yield. So it's usually the theoretical yield that is determined from stoichiometry. Okay. So, okay, you have another lecture. Okay, so thank you so much. So I'm going to send you the slide and the recording. So I wish you all the best in your exam. Another lecturer will be coming in by Wednesday. So I'm sending you the slide. So please try as much as possible, go through the slide, go through the recording, and I'm sure you will be good. Thank you and have a nice day. Please put your details on the chat. Likewise, those on YouTube, also put your details on the chat so that when I download, I'll be able to get all the details. So thank you very much and have a nice day. Please, I'll give just in the next 2 minutes for those that have not put their details on the chat, both on Zoom and on YouTube, to do that now before I log everybody out. Okay. Good morning. Lovely.